Okay, so our final test on this lightning tour of statistical test is the chi-squared test. Now, what the chi-squared test does is it measures association between two categorical variables and whether they're independent or dependent. Now, what does that mean? Well, let's just have a look at a quick motivating example. So imagine that I'm a manufacturer of cell phone games and I actually am a bit worried that I've got high brand awareness among males, but low brand awareness among females. Now let's have a look, and basically I do an experiment. I get lots of males and say, "Do you know about my product?" And the same with females. And then I kind of do this, which is what we call a contingency table or a cross classification table. I literally just put the counts in a table. So for males, I count the number of people who could identify and couldn't identify. And again, I do the same for females. Now let's first look at the rows. The number of males who could identify is well over twice as much as the number of females. But when it comes to could identify, then it's the other way round. So this is not even. If we expected these things to be independent, we'd expect these ratios to be pretty much the same. We could do the same going down. If we look at males, could identify to could not identify is about, 2 to 1, 95 to 50. But females is like, almost 3 times as many could not identify as could identify. So we think there's some association. These guys are not independent. So these guys are probably associated, which is another way of saying they're dependent on one another. Now note with the chi-squared test, we're not actually testing any sense of direction. So we're not testing if male gender causes brand awareness or if brand awareness causes gender. We're just purely testing association. Now, if they were independent, so we'll say if independent, then the expected values would be, and we're going to call this the expected value for cell I and J. So this is just the row, and this is just the column. And this is going to be the row total times the column total all over the total n. So this is what we'd expect if they're independent. And this actually flows from the stuff you did in Business Stats 1, which is, this is the row total for 1, which is that if probabilities are independent, you can multiply them together. Now, again, if I was teaching this in a stats class and I had a lot more time, I'd probably derive this equation from first principles. You don't really need to know it for this class, but the whole idea is the more skewed that our variables get, we've got this ratio of 2 to 1 and 1 to 2, the further we get away from having similar ratios, then the more associated and dependent. And this expected value is just say, hey, we had 300 items. Given if items were independent, this is what we would actually expect. What we'd actually expect to get. So let's go, actually, before we do our example, let's go back. So the chi-squared test, which again, we're not going to do it by hand, our null hypothesis is that we're independent. And our alternative hypothesis is that we are dependent. Now this guy here, these are just the cell counts. So let's go back for our previous example. Whoops, we should be going forward. The cell counts here, N12, is going to be, say, 95 in our example. And we're going to have, if you were doing this in stats, we'd have a lot of fun. basically saying, we'd calculate all the expected values, then we'd subtract them from the actual values, and kind of the further we are away from independence, then the bigger the chi-squared value. So we will say for this class, the bigger the chi-squared, the more dependent. Now, interestingly, the first time I taught marketing research, this was in my PhD at Rutgers, I actually set a chi-squared and made my students by hand. And I think I set a 3 by 3, which would require 9 of these calculations. And I actually made one of my students cry in the exam, which made me feel really bad. So this is maybe one reason why I concentrate on the computational stuff these days. Okay, so we kind of get the idea. I just want to do what I've done with all my other examples. And I just want to kind of quickly just show you the chi-squared distribution on the pen, on my whiteboard. So let's remove the previous one. And let's go with a black pen to start off with. So the chi-squared, it looks a little bit like the F distribution. It's kind of almost between a normal distribution and a F. And if you're into statistics, this in fact is a squared Z distribution. So we have the chi-squared values on the X, and this is kind of the probability. And again, to the right, this is the chi-squared gets bigger. So the bigger we get, the more dependent. And again, we get an alpha and we get a rejection region. So again, the type 1 error, the smaller the alpha, then the harder it is to, for us to get across that line and significant. And we'll actually have a chi-squared kind of alpha. I'll call it chi-squared star, which is the critical value. And this has, again, if you were doing this in stats, you'd look it up in the table at the back of your book. This has this has R minus 1, C minus times C minus 1 degrees of freedom, which you don't really need to know for this class. So in that example, actually, we had 2 rows and 2 columns, so it'd be 1 times 1, so we'd have 1 degree of freedom. So that's what happens if you have to look at the chi-squared in the back of the book. But luckily, we're doing it all in SPSS, so we don't have to do it. So again, imagine we have a chi-squared, and obviously this is not in the rejection region. So we fail to reject because it's smaller than the chi-squared. So again, we're going to reject H0 if my chi-squared is greater than my kind of chi-squared, my critical value for alpha with R minus 1, C minus 1. Sorry, I hit the button on my pen. Okay, that's terrible, but that's R minus 1, C minus 1. But at the same time, this value in red is my P value, the value more extreme. And again, as we go to the right, eventually the P value hits the alpha, and we cross into rejection region, it's less than alpha. So we also reject H0 if P is less than alpha. So again, this is why it's easier when we do it this way than how we did in business stats, because it's pretty much we're ignoring the test statistic and we're doing it the same every time. We reject if P is less than my alpha, and SPSS will give me my P. And just for consistency with my other methods, say we have something down here, this is a very small P value, so this is going to be the P, say, equals 0.005, which is less than 0.05, so reject H0. Okay, so let's kind of put that back. And so I've got a little data example for you. It's a fun little example. And basically, I think you all know this story of the Titanic that sunk. And I've got a data set that has the actual passenger log of the survival and information on these people and whether or not they actually survived or not. So we have what we're trying to do. And again, this is with any of the statistical tests, we're assuming a random sample. And this is the whole passenger log. So in a way, we're almost assuming this is like a random sample of a hypothetical passengers who their ship sinks and whether they survive or not. But we can actually get some useful information out of it. So we have the class of the passenger, we have whether they're male or female, and we have whether they survived. And what we're going to do is we're going to see if there's some association between this, between whether or not there's an association between the class, whether they're not survived, and also we're going to look at the association between gender and whether or not they survived. So we actually have the data set, and at this stage I'm going to go over to SPSS. Okay, so we have the Titanic data set here. This is the actual passenger log from the Titanic. I guess it's we don't have the same privacy problems given it's that most these people aren't around anymore. Notice at the time that this guy was actually the richest person in America, and apparently he just like started this society scandal before the Titanic like left by dumping his wife and kind of taking it with someone else. So this was actually a real this was like a real passenger log. So this said again, this guy was like the richest person in America at the time. And that, in fact, didn't help him survive. If you look at the articles from the time, there's a story about him and, how he tried to get on the lifeboats, but they wouldn't allow him on the lifeboats. But just as an aside, again, we have the whole passenger log here. We have their class, whether it's first, second, or third class, whether or not they survived or not, their age at the time, and their gender, whether it's male or female. So let's just kind of go through and do the analyses. So we've got analyze, descriptive statistics, and we're going to use the crosstabs functionality. Remember, this is what we used when we were creating these two-way tables. The contingency table I talked about is just really the two-way table we talked about in chapter 11. So we're looking at whether class is associated with survival. And what we're going to do is we also want to display clustered bar charts because this kind of gives us some nice visual information. And we're going to do the chi-squared statistics, and we're going to do the phi and Kramer's V. I'll talk about this when I go through results in the slides. Click OK. And we notice SPSS gives us the actual, so the data we have is kind of in long form. The data we have is basically we have the whole data set. But this provides a two-way table, a contingency table, where we're just summarizing a count by the class and whether they survived or not. And you can kind of see, there is a pattern here. So in the first class, 200 people survived and just over 100 people didn't. So nearly twice as many people survived as didn't survive. But in the third class, it's like 3-to-1 in the opposite direction. So again, there were not enough lifeboats for the people in the lower classes. So again, we can see this in the bar chart. We can see that in the first class, more people survived than didn't survive. And by the time we get to second class, this has changed. And by the third time we get to the third class, it's changed dramatically. So this is another thing when you do a chi-square test. Quite often, just have a look at a bar chart to have common sense. And even if the heights are different, if we're independent, the relative heights should be somewhat similar, which they're not in this case. So let's kind of go back to We've just done the clustered bar chart. Let's have a look at the results. So we have the contingency table, and then we have the chi-squared test. So going back, remember if our p-value is less than 0.05, then we reject the null hypothesis, i.e. we have some evidence of association, there's evidence of dependence. Now again, just be careful, because depending on the textbook, it's written different ways. Generally, it would be independent, dependent, or not associated, associated. Associated is the equivalent of saying it's dependent. And if the p is greater than 0.05, then we don't have enough evidence, so we fail to reject. Now look here, the p-value is 0.00000, which is the number of significant fingers we get in SPSS, so we reject the null hypothesis. It was pretty obvious. There is an association between class and survival. You know, looking at the bar chart, that is really, really obvious. Now, the thing is, when you have a big sample size, when you have a lot of data, you can get a significant test very easily, but it doesn't necessarily tell you how strong that test is, how strong that effect is. So what we could do here is we've got something called Cramer's V, which is something called this is not going to be in the test, the Cramer's V. But I think it's kind of useful. Something called an effect size, and this tells us how strong the effect is, regardless of the size of the data set. So here we're just doing chi-squared divided by some measure of the size of the data set, and then we're square rooting it with 0.1 small, 0.3 medium, and 0.5 large. So this is a medium effect. Again, if we have a really large data set, we're probably going to get significant even for small effects. So this can kind of give us some extra information. Okay, so we're actually going to go back, and I think I set this on the actual practical, but we're going to go back and just do it again. But we're going to now do gender. So again, descriptive statistics, crosstabs. Now we're going to replace class with gender or sex. And this is male and female survival. And we can say that most females survived and most males did not survive. Again, I guess this was like the 1910s. People were like, it was kind of quite a gendered society. And it was generally thought that the females should be allowed on the lifeboats first. And again, we can see here the actual figures in the contingency table of females, 3-1 pretty much survival, and males almost over 4-1 did not survive. And again, look at this chi-squared value. It's absolutely enormous. It's 365. My p-value is 0. And let's go a little bit further. We can see that the Cramer's V is 0.5, so that's actually a really large effect. Okay, so the last little bit is kind of perceptual mapping, and we've already covered this a lot. Basically a two-dimensional visual representation of data. Now, you can do a lot of perceptual mapping techniques in SPSS. They're not really, this isn't done in the book, and it's something I like, but it can get, you know, it's quite a bit of extra material, so I've left it off. But if you want to kind of understand, here's just kind of an example. This is exactly what we did in the first few weeks. You know, we're rating kind of fast food places on the freshness of the food and the food temperature, which seems a really weird way of actually doing a marketing analysis to me, but I could blame the textbook authors. And we're basically, you know, we could segment, we could say Wendy's and Backyard Burgers are the same, Hardee's and Arby's is the same, McDonald's and Burger King is the same. Food temperature, yeah, I don't quite get that one. But we did a lot of this earlier in the class, and I said I'm not going to implement a computational version of this, but I can, if anybody's interested, just email me, and I will kind of run through you and give you some instructions in SPSS. Okay, so that's about it for this week. Thank you for listening.